So we're talking about fluid dynamics. We have talked about Bernoulli's equation both longitudinally and normal to the streamline. We did a problem with a so-called free jet, which was the idea that you could write Bernoulli's equation upstream and downstream in a bucket that has a hole in it. And the interesting observation we had was that the velocity at which fluid comes out is a proportion of the height of the fluid above the orifice, and also for the free jet as it arcs out of there, a cumulative amount for the difference in elevation between the upper free surface, which is charging the bucket, if you like, and the location below it. So what I thought we'd do today was work through some examples just to give you some feel for how to solve these problems using mainly the linear along streamline Bernoulli equation. Introduce one other concept, which is continuity, which is basically volume rate in equals volume rate out if you're not accumulating things, and then see if we can apply it to a variety of different problems. So I think the best way to do this is to kind of talk about how to solve these rather than go through them numerically. And so we'll just walk through a few problems and talk about them in some detail as to how we do them. So this is a question that's basically asking if you have a bucket full of water and a free jet coming out of it. The free jet comes along a hose that's inclined at some angle, pointing upwards. And basically the question is, what is the height to which this jet would go? And a related question would be how far it would go as well. It's made a bit more difficult by the fact that you had a hose here. If the hose here was zero, then it would be a simpler problem to solve. And there's been an exam problem like that, I think, in the past with no hose length to define. And I guess there weren't enough hints and tips on this one today. And so the question is, how do you solve that? And so, as in all of the problems that we've tried to solve, you can write Bernoulli along a streamline. Certainly, on a streamline would be this green line here that goes through the hose ultimately. So this would also be on the streamline. This would also be on the streamline, and this would also be on the streamline. So all of those points would be on the streamline. So you could write equations at those points if you wished. But the essence of this is to be able to figure out first what the velocity is that's coming out at point 2. So if you write Bernoulli between points 1 and 2, then you can certainly define the things you know. What do we know here? We know pressure at this point. We know elevation of this point. And if it's a big tank, then the velocity is 0, right? So we know pressure is 0 if it's atmospheric. Elevation we know. And if it's a big tank, then velocity is 0. At this point, we need to know what? We don't know the velocity, but we do know the fluid pressure for the same reasons as we've said before, that this is 0. And we know the elevation because we know this length as a function of the angle. It's made more difficult by that, but we certainly know the elevation z. And so that gives us some ability, for instance, to be able to calculate V2, right? So we have one equation, we have only one unknown, and so we can solve for that one unknown as a function of the other ones. So we know what V2 is. And so we can think of this in terms of how would we then solve for this point here. So what we could do is we could also write it, we could do two things. You need to realize the physical setting of this. You could do one thing to be able to say, for instance, something about what the ball does as it goes up into the air. Oops. And this is no different from a jet, right? So as you throw it up, it has gravity acting against it, and it will arc up, and it will stop. If I throw it up to some height, when it comes back down to my hand, it's traveling at the same velocity in the opposite direction as it was when I sent it up, right? Because it's gone up to its arc, stopped, and come down. It's the symmetry in the arc. The other thing I could do is as I throw it up, I could shove it sideways. So I'm not sure how I can do that. I guess I could try this. So I could do that, not very successful. But the sideways travel shouldn't in any way affect what it's doing up and down, right? So it's doing this, going up to a peak height and coming down, would be one arc to one height. If I give it the same upwards velocity but shove it sideways at the same time, I'm not doing it very well because I'm not throwing it up, it should go up to exactly the same height but come down further over. And so what we can do is we could divide this into just the component of this which is going vertically. And we could write an equation vertically to say exactly what the limit of this height would be as if you squared it up vertically. And if you wanted to, you could write Bernoulli for that at this point, right? So in this particular case, if you knew what the velocity was going upwards, you could write an equation to do that. The other thing I suppose you could do is you could just write an equation of motion, which is what? Velocity is equal to v0 plus az times t, right? Which is equal to the change in elevation with time. You could also write this out as the change in elevation is equal to v0 plus a. You've seen this before in your mechanics books, right? Just dt. And if you integrate this, you end up with something that looks like elevation equals, what's the integral of this, right? This is the, assume this is 0, half a t squared. And so if you know, for instance, how high it goes, which we don't know yet, then you could calculate what the time would be. And so I guess I've jumped ahead a little bit in this. So if you know, for instance, how high this can go, you could calculate how long it would be in flight. And if you knew how long it's in flight, you'd be able to calculate how far it had gone, right? So there's two parts. They don't ask you the second part, but you could do both. So what you could do is, since we know the velocity at this point here, you could write the behavior at this. What's this? Hello, Dylan. How you doing? You could write the expression here. So if you write this as being equal to, we could write it between P2 over gamma plus Z2 plus V2 squared over 2G is equal to the pressure at point 3, unit weight, the elevation at point 3, and the velocity at point 3. We know, for instance, that the vertical velocity at this point has to be 0 at this point. We also know, for instance, that the velocity in the direction of 2 has to be from continuity requirements along this point. So we know that V2, let's see, I guess I wouldn't have done it this way here. Since we know that the pressures at this point, we know the velocity at this point, point 1 is 0, and we know the elevation at this point. And we know the pressure at this point here is equal to 0 also. We can get the magnitude of the velocity at this individual location here. So if we solve for that, we get, yeah, I guess I wouldn't have done it that way. I'm trying to think, how would I have done it? I think the easiest way to do this is to write it in terms of the vertical velocity here as V2 y and yeah, actually I wouldn't do it that way. So I'm confusing myself in this. Yeah. Well, the velocity in the vertical direction at point 3 is 0, but the velocity in the horizontal direction is going to be equal to the same as the horizontal velocity here.
No, like you have the pressure 3 circling down there from Bernoulli Equation.
That's 0, yeah. So the velocity in the vertical direction has to be equal to 0 here. And so I'm trying to back this out. So we don't know that this is the streamline velocity in this particular case, which we can get. And so by writing at these 2 points, not from point 2 in this case, I guess from point 1. And in this particular case, this allows us to get the streamline velocity as a function of, okay, yeah, right, so the streamline velocity is given by this. We know the height that we have here, just from this expression here. And so I guess the only thing that we don't know is the magnitude of this height here, which we can solve for. The streamline velocity here has to be the same as the velocity coming out of the hose here. Has to be the same as the component of the horizontal velocity coming out of this hose. So this component here, from the analog of throwing the ball up, so the velocity in the horizontal direction at this point, which we can calculate here from this, right? So this, if it's going up in some arc, has some vertical velocity that's throwing it up in the air from my hand. If I shove it sideways, then it's also going through the same arc. It has the same horizontal velocity all the way it goes along here, which is the same component as it comes out of the hose. So it comes out of here with a vertical velocity, and it comes here with a horizontal velocity. The resultance of those is actually the velocity along the arc. The horizontal velocity has to be the same all the way as it goes along here. So as it comes up to the top of its arc, it has to have the same horizontal velocity as it had when it left here. It'll be the same horizontal velocity when it hits the ground as well. So the one thing that we know when it comes out of here is it has some streamline velocity V2. That streamline velocity V2 is a horizontal component and a vertical component. If we realize that this horizontal component is exactly the same as the streamline velocity here, then we can write Bernoulli's equation to be able to figure out what the velocity is here in terms of things we know, which is writing it between point 1 and point 3, which is here. And so the only thing that we don't know in this equation is, well, two things we don't know in this equation are this velocity here and this elevation here. This is h, right? And so this is this expression here. So now I know where I'm going. And so this is the height of the tank. This is what we don't know. This velocity here is the horizontal velocity as it leaves the nozzle. If we know the horizontal velocity as it leaves the nozzle is the same as the streamline velocity here, then we have a value for V3. So V3 is just equal to, we can substitute, it's equal to V2, what would it be? It's cosine, V2 cosine theta. And so since we know V2 in an absolute manner, we can substitute that for V3. And then in this expression here, the only thing that we don't know is h, and we should be able to solve for h, which is kind of complicated, but that's the principles. So the idea is that in a streamline, the only two things that are going on is that it comes out at some velocity, it has a vertical component, and it has a horizontal component. You can break them up into those two, and if you're thoughtful about it, then you can actually see how you'd use those in some useful way. So what this gives you then is the ability to be able to calculate what h is. So you can calculate what h is. So the question is, how would you calculate how far it's gone? So one way to do that is to figure out exactly how long it takes to go up to this height. Not in this question, but one thing to do is, how long does it take to go up to this height? Well, you know that when it comes out at some velocity v0. So it would take an arc that would look like this, right? If you draw it just going up and down. So here this has some velocity v2z, I guess, upwards. What's the velocity here? Right? Yeah, has to be 0. And so it's symmetric. So it starts off at some velocity here, which is something you know. It goes up to the top of its arc, it stops, and it comes down. When it comes down, it's going at exactly the same velocity in the opposite direction as it went up, right? There's a symmetry of this. And so what you could do is you could use dropping a ball from this point here to some height, so you know h. If you know h, you can use this, and this will give you the time. So if you know the time that it takes to go up to the arc and come down, that's the same amount of time it takes to go from this point to this point, if you do it from here, right? And so you could get the length as just equal to the velocity in the x direction times time, right? Length over time times time gives you length. And so just ways of thinking about problems, right? So you have to rationalize it. So a bit more complicated than it needed to be because of this hose coming out of here. If it was just a straight point jet coming out at some angle, it's much easier because you don't have to mess around with this length. But the basics of it are, it comes out of here, it has a streamline velocity. In Bernoulli's equation, it's always a streamline velocity that we write, but you can divide that up into components just like you can forces, and then think about it in useful ways. So that's the way of dealing with that. So an interesting problem, I think. I mean, I think the other thing that comes out of this is, the question is, what happens if you pointed this hose directly upwards? How high would the hose go? And I think you could do that just by drawing, a Bernoulli equation that would have a streamline that would basically do this. If you write Bernoulli between points 1 and points 5, maybe, what comes out of it? You have Z1 plus pressure 1 over unit weight plus V1 squared over 2G is equal to Z5 plus P5 plus V5 squared over 2G. And so maybe you don't know what this height is. You could ask yourself the question, what is the place where the streamline velocity is equal to 0? And so you know Z1, you know P1 is 0, you know because it's a big tank that V1 is also 0. You don't know Z5, but you know the pressure at this point has to be 0 as well, and you know you're looking for a place where the velocity is 0. So the only solution where that is true is where Z1 and Z5 are the same. So perhaps not surprisingly, if you squirt stuff out of a tank which is static, it goes up to exactly the same height as a tank. And you can think about that. If you had a pipe coming out of the tank and you pulled it up higher than the tank, you know that the water rise in that pipe would be level with the surface of the water, just from your manometer equations. You know that if you can go from one point to another within a connected path, and you end up at the same elevation in those two locations without having to go out of the fluid, you know that the pressure in those two things is the same, on the same horizontal line. So it is static because it's not flowing. If you had the pipe that was higher than the tank, then of course it's static because it can't physically get out of there, and the equations are no longer the Bernoulli equation that you have to use because there's no velocity. You could use the static equations. But you can also use the Bernoulli equation to do it because the velocities are 0. So by de facto, if you like, the Bernoulli equations, which are dynamic, also count for the cases if the water's not moving as well. It would have to, right? Makes sense. Okay. All right. So that's the solution for that. So other solutions. 2 jets. So I think the question is, you have 2 jets banging into each other. They destroy their momentum as they flow into each other. One's a free jet, which is flowing vertically downwards. One's a jet which is being powered by an overpressure. How do you solve for the height of the tank that you'd have that would give you this position of the free jets intersecting? So what do you do? Realize what the boundary conditions are. Realize that you can write Bernoulli equation at a variety of different locations. Certainly you know behaviors here at the top of this tank, although you don't know its absolute height. Certainly you can write behavior at this point here, where you can think about streamline velocities, and certainly you can write behaviors here. So the top tank, atmospheric pressure, big tank, velocity 0, and the elevation relative to some datum. You can choose your datum, but it's probably easier to take it from the bottom. In this case, it's done from here. And you have an elevation of the tank. So this point here, you have an overpressure, which is larger than is prescribed. Again, no SI units preferred. A big tank, so velocity is 0. And an elevation of this point also, which is not 0, which is above this. And finally, this point here, you don't know what this is, but that doesn't come into play here. But you could also write Bernoulli at this point here as well. What do we know about the pressures at this particular point? Well, let's figure it out. We know for sure that the velocities at this point are 0 because it's being destroyed. What else do we know about the pressures at this point? Oh, okay. Well, let's go through and write the expression. So these are the unknowns. So I guess this is point A. So you could write expression between, in this case, this point and this point. It's on the streamline, right, as you go from here to here. And so pressure at point 2, velocity at point 2, elevation at point 2. Pressure at point A, velocity at A, and elevation at point A, which I guess we know, right? So ZA is equal to 20 feet. We don't know this. Stagnation because the jet is hitting something. Big tank, so velocity is 0, atmospheric pressure, and a slightly unknown elevation because this is equal to 20 feet. Whoops. This is equal to 20 feet plus h. So this is the expression that comes out of it. We don't know what the pressure is that's developed at A because we're destroying the fluid as they hit each other. And so we have a relationship at this point. We can also write Bernoulli's expression between point 1 and point A as well. So point 1 is this, and point A is this. We've said that it's a big tank. It's got an excess pressure in it, and it has some elevation, which we know. This is what we defined before, which we don't really know, but we'd like to figure out, stagnation. And we do know the elevation at this point, and we also know that we're killing the velocity. So we have, in this case, we have 2 equations and 2 unknowns. And so what we could do is we could inject this value of the unknown pressure here into this expression, which is defined just as a function of h, and then try solving it. And if you solve it, you end up coming out with the value of this remaining height of the tank. So it's just a matter of being able to figure out exactly what you know and what you don't know and go about evaluating the unknowns. And so what you do know in this case is that the velocities have to be 0 because they're hitting each other, like 2 cars on the freeway, basically destroying their momentum. The velocity here is 0. So it's really no different, actually, to it hitting a wall, right? So if you think about just the jet coming up from below and hitting a wall, the velocity that hits this point is a stagnation point, just as the converse for the jet coming down and hitting that has to be a stagnation point as well, by definition. So the issue is that you just need to be able to write enough equations to be able to solve for the unknowns that you have, and know where you know the different behaviors. Okay? Again, in units. There's one extra. So one way that you can solve problems where you have 2 unknowns in a single equation is you can use an extra constraint. And the one extra constraint that you can use is the so-called continuity expression. Continuity or conservation of mass, which are both very fancy terms for something very simple. And it just says that if you take a streamline for Bernoulli, so say the top streamline is this, it's going through, it's representing flow through your system, then a streamline means that a particle of fluid is going along this length. So by definition, it means also that there's no normal velocity to that particle track. So it's basically a no-flow boundary. So you can think of this as a no-flow boundary. A streamline is a no-flow boundary. If you take another streamline through the system, which is this lowercase, exactly the same applies here, and that is that no fluid can pass across that boundary because it's only going along the boundary. And so that basically isolates a volume. And so now, if you look at the velocity going into that stream tube, if you like, and multiply that by that area, you get a volumetric flow rate. If you wanted to, you could also multiply it by density. So you could also do a mass flow rate if you liked, which is equal to the volumetric flow rate times the density, which is just equal to V1 A1 times density. So conservation of mass is the correct way to do it, but for our cases, because it's an incompressible fluid, conservation of mass and conservation of volume, if you like, are the same things. And if you look at the downstream location, you can write the volume out is equal to the velocity 2 multiplied by the area over which it flows. This is the area. And so the mass flow rate down here at point 2 is also equal to just the volumetric flow rate multiplied by the density. And so the amount of fluid that comes out of here in a given time is given by this expression. And it's the same as pumping up a tire. When you pump up a tire, there's no outlet for it. It goes in, and so there has to be some change. The change is that the mass changes because the density goes up because the air compresses and fluid is accumulating. But you're accumulating fluid by changing the density, and one of the requirements for Bernoulli is that the density doesn't change. It's incompressible. And so to guard against that, basically, any flow rate that goes into here, if you're not accumulating stuff in this flow tube, has to flow out in exactly the same measure. And so we can write that Q1 and Q2 are the same, and then we can use that to be able to constrain expressions. So typically the way that we write this is that we write it in terms of velocity at point 1 times the area at point 1 is equal to the velocity at point 2 times the area at point 2. One has to be an entry point, and one has to be an exit point from the same system. And so if you end up with a Bernoulli expression that has two unknowns, and you can't therefore solve the equation, then maybe you can relate the velocities at the upstream and the downstream location in terms of their areas to be able to solve it. And so that's one simple way to be able to solve Bernoulli's expression. Do you want to do that right now? No, let's skip this one and go to this, because this kind of illustrates the point, I think. And so this is an example. If you have a tank with air in it at some pressure, it is air, so it is compressible, and it has an exit nozzle of some diameter and a tube that has a different diameter that supplies that exit nozzle. The tank is big, quote unquote, which means the pressure doesn't change. Just the same as a tank full of water that's a big tank, the velocity on the surface is 0. It's the same, it's kind of code for the fact that pressure doesn't change. Has a diameter as the hose as you come out, a smaller diameter nozzle. Pressure in the tank remains constant. It's at 3 above atmospheric pressure, which is what gauge means. And everything else is at standard temperature and pressure. What is the flow rate in the hose? So I guess the question is, what is the velocity at point 2? So if you write Bernoulli at these locations, what do we have? Do we know any of these components? So let's just write those out. V2, P2, and Z2. Okay, so what do we know? Well, they're all on the horizontal line, and so we can take a datum through there, and if that datum is the same datum, just easily just set it equal to 0. Could be any number, but the fact is that they're equivalent to each other. So 0 is the best number. Big tank, stagnant, so set the velocity to 0. The pressure we know is 3 kilopascals, which is equal to, for instance, 104.3 kPa, right? If we did absolute pressures. And the reasons that we might use absolute pressures is because we're dealing with a compressible gas. We don't know what the pressure is at this point. We don't know its velocity. and we know its elevation. So we can't write Bernoulli between upstream and downstream. We know everything here, but we don't know two things here. So we can't write Bernoulli straight away and solve for velocity. So we need some intermediate step. And so what do we know at the downstream location? We know the pressure is atmospheric. So depending on whether we use gauge or absolute, if we use absolute, it would be 101.3, I think, right? But you could also use gauge pressure as well. And we don't know the velocity. So we know everything here. We know everything but one thing here. So we could certainly solve for the velocity v3. And so if we write Bernoulli's expression between these 2 points, we can get v3 as a function of the upstream behavior. But in this, because the velocity v3 has a density in it, the density at that point 3, we don't necessarily know what that density is. We can presume that it's different from this because, of course, the only thing driving this flow is the change in density from the upstream where it's pressurized to the downstream where it's a different pressure. And we know as it goes downstream and changes pressure, it should expand. And so it should be less dense. And so we need to be able to use the appropriate density at this point relative to, so that this is the density at point 3 because it comes from this side of the expression. So we know this is whatever the pressure in the tank. We don't know what this is, but we know that could calculate what the density is. So we could do that if we wanted to. But we could also now, since we know that we think we can get the velocity here, is we can say something about the velocity at this point 2, right? Because from continuity, we know that the area at location 2 multiplied by the velocity at 2 has to equal the area at point 3 multiplied by the velocity at point 3. So if we know this, and we know both of these cross-sectional areas, which we know from the geometry, then we have a fighting chance of being able to figure out exactly what this velocity is, which is what we want. And so it's only complicated in this case by the fact that we need to include a density in here, which is the density at point, this point 3, which we could include. Actually, or is it the density at point 3? Has to be the density at point 3, yeah. So if we take the expression for this is writing between points 1 and points 2. We know the pressure in the tank. We don't know the pressure yet at point 2. We want to also know what the value of the velocity is at that point. We can write the magnitude of the density, in this case in the tank, as a function of the pressure in the tank. And so we can get the density in the system to be able to define that if we so wish. And we can use that to be able to calculate. So is that right? Why is this not the density in the at point 3? V3. So it's written between point P1. This velocity is finite. V1 0. Yeah. Well, certainly we can get this, the density as a function of this.
Dr. Elson?
Yeah.
So it says in the assumptions that we're assuming steady and viscid and incompressible. Does that mean that the density would be taken to be constant throughout the problem?
Can't be, because it won't flow, right?
Right.
Because if this is a tank of water that's pressurized, and you open the spigot, it will flow briefly and stop because it has no compressibility. It's the compressibility of the air that kind of sustains the flow. It's just like if you filled a tire with water and you took the valve off, then you'd get a small spurt of water for a while, very briefly, then it would stop, compared to what you do if you puncture a tire.
So if we have a gas, how can you assume it to be incompressible?
Well, you're violating some of the requirements for Bernoulli, but not very much. expression. So we can actually use Bernoulli to solve problems where there's viscosity as well, even though it's for inviscid conditions. And so you can tweak those absolute. The absolute requirements are that it's incompressible and inviscid, but you can actually get away with assuming that it's slightly compressible in some cases, so long as the pressure changes aren't large, I guess. And of course, this isn't a steady problem. The other thing that you're violating is that once you open this valve, it flows for a while, then it stops. It doesn't flow indefinitely as all of our other problems would be. So if you looked at this system at time 0, when the valve's just opened, and then you looked at it 10 seconds later, the pressures in this system, the pressure here would have changed, right? Because you're losing fluid and you're not replenishing it. And so you're violating the steady state conditions as well. So anyway, let's get back to this. So we can get the velocity if we know the density in the system. The density, I think it should be the density at point 3 because the velocity at point 3. So anyway, so that's an interesting twist on that. Perhaps it doesn't make much difference to the result. And if we know the pressure, we want to calculate the pressure at point 2. We know the pressure at point 1 is 25, well, it's not 25, it's 3 kilopascals. And we want to be able to calculate the velocity at that location. If we know the velocity at point 3, we know the velocity at point 2 as well, so we can use this. And so in this expression, the only thing that we don't know is the magnitude of this pressure. And so, I'm trying to get through. So this is solving here. This is solving for the density. This is substituting the density into this expression where we know the pressure to calculate the velocity at point 3. If we know the velocity at point 3, then we know the volumetric flow rate. And is that all that's being asked for? Yeah, I guess the flow rate is being asked for. And if we know this flow rate at point 3, then we also know the flow rate at point 2 because V2 is equal to V3 A3 over A2. We know both of these areas. We now know this velocity here. And if we know this velocity here, we can calculate the pressure at point 2. And so, convoluted, unfortunately, but a way of being able to solve it. So the main points, I think, are that in defining behaviors, you need to be able to write Bernoulli at different locations, figure out when you know enough to be able to solve it. Here you know everything about it, so you have all 3 components known. Here you have 2 components unknown, and here you only have 1 component unknown. And so certainly you can solve between 1 and 3 to get the value of this velocity. Once you have the value of this velocity, you can certainly write the velocity here just by continuity. If you write the velocity here, then you also have, you can write Bernoulli between this point and either of the 2 other locations because you only have 1 unknown in the system. And you can solve for P2. And so a little complicated and convoluted, but doable nonetheless. So have a look at those. Yeah.
So the reason we're using the density of F1 is that because it wouldn't be favorable.
Say?
When you were calculating for B2, the density that you put, you said it should be 3, but we're using density F1.
Yeah.
Is that because it doesn't make a big difference?
I don't know. I think it should be at point 3, don't you think?
Yeah.
So the expression that comes out is going to be this pressure. This is density at 1, and so we're writing this expression here and this expression here, and so this velocity is, yeah, this one drops out, right? So it's 0. So it is the velocity, the density at 3. So this density should be at atmospheric pressure, which should be the density at. So I think if you do this as, if I was doing this, I would use this as 0, and I'd use that. Yeah, it's not going to make much difference, I don't think. But I think, strictly speaking, it should be that density. So, and the rest of the calculations are there in just what we've done. So, a bit more complicated than maybe it needed to be. The other thing that, the reasons that we're interested in Bernoulli is that it also as we know from talking about pitot tubes, for instance, it allows us to be able to calculate flow rates relatively straightforwardly. So it's very easy to make a pressure measurement. You make it with a pressure transducer, which is, we've talked about before, is just a membrane that has a pressure acting on the outside and some set pressure on the inside. And if you change the pressure on the outside, the membrane deflects. And if you measure that deflection, maybe with a strain gauge, which gives you a voltage signal, you can calibrate that voltage signal to represent the pressure. And so it's very easy for us to measure fluid pressures with a transducer or with manometers, as we know. And so if you want to measure flow rates in flowing pipes, for instance, one way to do that is to use the idea of the Bernoulli Principle, or the Venturi Principle, I guess. And that is that if you're flowing fluid down a pipe and the pipe diameter doesn't change, then it keeps on going at the same rate because of what we've talked about in terms of continuity. And also you can show that using Bernoulli. But if you constrict the pipe, then what you're doing is you're changing the area of flow. And so from thinking about that, if you write A1 V1 equals A2 V2, if this area goes down, then to correspond for that, this velocity has to go up, right, to keep the same constant. And so that's all that is implied by Venturi. But the implications of accelerating this fluid in going from a slower velocity at point 1 to a higher velocity at point 2 is that if you have to also satisfy Bernoulli at both of those points, so you can write Bernoulli at point 1 and Bernoulli at point 2, and they are at the same elevation, so we don't care about this. But if the velocity goes up, then the pressure has to go down. And so if you plot pressure along the course of this, then you'd see that the pressure would go down in the Venturi. It's kind of like the same principle as flight. And if you measure that change in pressure at this particular location, you hope that you can index this pressure relative to the velocity. That's basically the idea. Of course, you don't want this constriction to be so large that it speeds up so much that it goes below the vapor pressure of water, in which case it will cavitate and you'll get bubbles in your flow, and you won't get very accurate readings. But you could, in theory, if you flow it fast enough and change the velocity at points 1 and 2, or change the velocity at point 2 enough, it could cavitate and you'd get vapor in your flow. And so that's basically the idea of Venturi meters. You can write Bernoulli's equation at two locations, upstream and down at the Venturi constriction. And if you measure the pressures at those two locations, you can say something about the velocity. You can imagine a variety of different meters, some of which just have a blockage in the pipe, some of which are much more gradual change. And the reasons for using progressively more gradual changes are that you don't have these kind of circulating effects, which make it much more accurate in terms of being able to make the measurement. But the principle is very simple. You can take a horizontal pipe. If you write Bernoulli upstream and downstream, you can apply continuity to get the changes in velocities as you go across it, which we've just said. And if you can combine these two expressions and solve them, you can define flow rate, which in this case would be the flow rate at point 2 at the constriction. I guess it would be the flow rate at both locations, wouldn't it? As a function of the cross-section area of flow, the difference in the fluid pressures between the upstream and the downstream location, and the difference in the cross-sectional areas across the pipe. And so certainly you can measure these as part of the pipe you have. Certainly you can measure these either by a transducer in the pipe, and certainly you know what this cross-sectional area is here. And so just by measuring this different pressure, you can calculate what the flow rate is. And the other interesting thing perhaps to note from this is that the only thing that matters here is the difference in pressure. Not the absolute magnitudes, but the differences in pressures that you have. And if you use that, you're able to get the magnitude of the flow rate. And so some examples that maybe we'll go through next time.